So yeah, this work is done by my undergraduate student, Adina Friedman, on desirable behaviors for companion bots and first-person shooters. So there's a little bit about human modeling here, because what we wanted to look at is just, think about companion characters in games. In the best case, they're really helpful and they enhance the experience. But, of course, there's plenty of examples of bad companions in games. They sort of burden the players. They lead to stagnant gameplay. And so there's a question of how you address this. And it seems like, the way it's typically done is just a lot of meticulous programming and testing, which, succeeds. And there's plenty of good examples of good companion characters in games, and there's some shown here. But, that takes time and effort. And, to some extent, we want to make bots more human-like, and there's kind of a question of how that, what that even means and how you'd even do that. So that's kind of some larger overarching questions, but what this is just focusing on is some more low-level stuff. So what are some basic behaviors that humans prefer? Sort of what outcomes do they prioritize, and what are the reasons for their preferences? So we did this study in Unreal Tournament 2004. Granted, old game, but it is a first-person shooter, and I think that a lot of features of the genre still persist in modern shooters. It has support for many multiplayer modes. We simply use team deathmatch, but you could imagine doing a similar study with others. And the other reason for doing it is that there's this nice interface called Pogamut that lets you control agents in the game via this mod called GameBots. And this was really heavily used in the Bot Prize competition, which wrapped up in 2012. That was a sort of a Turing test for AI GameBots. And I was on one of the teams that actually won that in 2012, so I had this experience. Now, for those that haven't seen the game, this is what it looks like. Typical first-person game, you're running around shooting enemies. Those are two enemy bots, and they just killed the player. And then as soon as you dive right back in, so you immediately respawn, and then, shooting, chasing. It's pretty, hectic. And we'll see here in a minute how, the enemy team, so the human killed one of those bots, but then is about to eat a missile in the face, right, from the other one. So very, quick gameplay. I think a lot of you are familiar with that kind of stuff. So what our study did, it's a human subject study, and we have two bots. And we wanted to contrast two extremes. And so one of them is more collaborative and team-focused. The other one is sort of more proficient and score-focused. We had 30 human participants. Everyone played around with each of the bots and then filled out surveys afterward that were rating the bots and indicating their preferences. So the first of these two bots, which we just called Jude, is hand-coded, and it's meant to be a bit more collaborative. This is sort of a priority list of behaviors, which mimics human collaboration a little bit, and it's not super complicated. The main thing to take away from this is that it tries to stay close to its teammate. Now, if it's low on health, it'll run off to find health. And if it sees an enemy, it'll engage the enemy and also chase it if it escapes. But in lieu of either of those things, it'll focus on staying near a human, presumably teammate. Now, the other bot in this study, which we called Ethan, is evolved. And this, as the picture might suggest, it actually is very proficient at killing opponents. It was evolved. It has a neural network combat controller. This is its sort of behavior list, which is much less complicated than the previous one. But the thing to keep in mind is that this very sort of first behavior, combat using a neural network controller, is complex because that handles all the combat behavior, and it's actually fairly proficient. In some ways, this bot is a stripped-down version of UT Squared, which is the aforementioned bot that won the Bot Prize in 2012. But it's a bit, we redid it from scratch and simplified it in many ways. And we didn't really care if this bot, interacted with the human teammate at all. It just tries to kill enemies, and that's it. And it was evolved using MMNeat, which is a variant of neuroevolution of augmenting topologies. MMNeat is sort of my version of it, but Neat's a very well-established algorithm. It's less frequently used now. The nice thing about it is that it evolves these neural networks of arbitrary topologies. But I wouldn't use it to evolve like the super deep networks that we're seeing now with RL. So for those that are a bit less familiar with evolution, you basically have a population of individuals, and you evaluate them, you rate them. The better ones get to create offspring, but the offspring they create are slightly modified. And so the modifications here are mutations for adding links between neurons, changing the weights of existing links, and splicing neurons along existing links. And there's also a clever way to do crossover in NEAT. As I said, I'm using MMNEAT, which stands for Modular Multi-Objective NEAT. Although we're only using the multi-objective part here, we're not using multiple modules. And so the way that this Ethan bot was developed is we evolved for 100 generations with multiple objectives, specifically maximizing team score, damage dealt by the team. And so those two are kind of aligned with each other, and then minimizing the damage received by the team. And we did a really small population just because it's kind of costly to do evaluations in this game. So only 10 networks, but we evaluate each one 3 times because of the noise in the evaluation. Individual trials last 2 minutes, and that's wall time, which is, once again, why we're doing such a small population. And what happens is you take one network from the population, you make 2 copies of it, and each of them are on a team together against 2 native bots. And after doing that for a while, we get a population. They have this sort of range of scores. We focus on the one that has the best team score, and we picked that particular network to be the Ethan controller. Now that's just sort of background for the human subject study I'm about to talk about. Now the parameters here are not like the raw screen. They are sort of engineered. These are really like neural network inputs. And some of them are listed here, the others are listed in the paper. You can see it in more detail. The GameBots mod that I use doesn't provide a visual like screen capture interface. And so instead we're falling back on more traditional stuff like sort of pie slices. That's an overhead perspective of the bot with respect to like where other agents are in different regions around it. Ray traces for detecting obstacles and various other things. Because the network controller is only used during combat, the outputs are opponent-centric. So the network outputs are for moving forward or backward with respect to the particular opponent, or strafing left or right around that particular opponent. And then there's an output for, do I jump now, do I shoot the gun right now? And so given that setup, we have these 2 bots, Ethan, the evolved one, and Jude, the hand-coded one. We do this human subject study with 30 participants. After each, they're filling out these surveys in Google Forms. We record their screens during the study. Because UT 2004 is an older game, everyone does a little 5-minute session one-on-one against a native bot first, just to like get familiar with it. And then they go against one of our bots, do a survey, go against the other bot, do a survey. The order switches depending on the individual, so we don't get any ordering effects. And we ask several questions, you know, what qualities you like or dislike about the bots. We have them rate various things on a 1 to 5 scale, which I'll go into more detail in a moment. And we ask for improvements and ask, you know, the reason for their preferences. So the first sort of just high-level thing that comes out is that 17 out of 30 preferred Ethan. That's the evolved proficient bot. 13 preferred Jude. This is actually not a significant difference. It's pretty close to like some like one, some like the other. So it's annoying. But if we dive deeper, what can we learn? Well, let's look at their raw ratings first. So these are the 1 to 5 scores. So this does reveal some significant differences. Basically, users thought that Jude was better at following, which makes sense. It's explicitly programmed to do that. They thought that Ethan was more helpful, and we're going to talk more about what that means later. They saw Jude more frequently, which once again makes sense. It's specifically following the human around. Ethan was better at scoring points. As I said, it's this efficient Terminator killing machine. And Ethan was also better at avoiding death. So clearly the user observations agree that Ethan was the more proficient bot. And all of these differences are significant. We then look at how every individual rated each of the bots. So we know what they rated them on these 1 to 5 scales, but did user A indicate Ethan higher in this regard or Jude higher in this regard? Which one did it think was the better of the two? And so what this here is saying is that 16 individuals, 53%, thought that Jude was better at following, whereas 9 thought Ethan was better at following, and 5 gave them the same rating, whatever that was. And what we did with all of these ratings is compare them with a binomial test, and it's a bit tricky to do that here because binomials for comparing like basically 2 possibilities, and so we have these ties. And so there's a question of what do? Do you ignore the ties, or do you split them up equally among the 2 individuals? We actually split them up equally, and that seems odd, but it actually makes it less likely to reject the null hypothesis in any of these cases. So we actually are passing a stricter test by keeping those numbers and dividing it. If we were to ignore the ties entirely, we would actually see even more significant differences here. So this is more conservative. But even under that comparison scheme, what we have is that Jude is, or rather Ethan is significantly better at helping, and significantly better at scoring, and significantly better at avoiding death. Now, Jude, the hand-coded bot, was better at following and being seen, but not significantly so. So we take this one step further and look at, okay, so we know which bot the human thought was better, and we know what their ratings were, but did they like that attribute or not? So what this is looking at is, whichever one they thought was better, was it the one they said was the better follower? Whichever one they thought was better, was it the one they said was the better helper? And we do the same kind of binomial split here, and the main highlights are that most people, or rather a significant number of people, preferred the better helper, and interestingly, a significant percentage preferred the one they saw more. And I think that one just speaks to sort of quirks of human behavior. It's like, oh yeah, I saw this bot more, therefore I like it more. If you don't see a bot, you never interact with it, and you just tend to like it less. Now, if we look at the reasons people gave for these preferences, we learn a bit more about how to interpret it. So some people like Jude. Why? Well, they emphasized the fact that there was more teamwork and the feeling they got during playing, as opposed to the objective results of getting a higher score. With Ethan, which was the better bot in terms of score, people just said, oh yeah, it was better at scoring and killing and avoiding death, therefore I liked it more. It was really good. And so we have people emphasizing different things. Now, here's a video of Ethan, which kind of highlights how it was doing. So we see that human is walking around, and there's an enemy bot, and there's Ethan on the left, comes in, just wastes that enemy bot, basically steals the kill, and then disappears. And so the point of this is that Ethan was definitely more proficient, but some people really felt ignored by this bot. They felt like what they were doing didn't matter, the game was too easy to win, and 14 specifically said that they wanted Ethan to follow them more. Now this quote here really sums up nicely. It says, as counterintuitive as it might seem, players often enjoy an ally that is good, but not quite as good as the player themselves. Players enjoy being the hero of the game. In contrast, people mostly appreciated that Jude was following them around. In terms of its combat, the combat was super simple. It just like rushes the enemy, and so people thought that was overly simplistic and aggressive. It was. And also, there's apparently some like weird sort of buggy issues. Like, for example, if the human stayed still, Jude would just get in its face because it wants to follow them and stay close. So it was a very simplistic mode of cooperation. And so one easy way to improve this kind of bot would be to sort of combine, Jude's more complicated decision tree with Ethan's more sophisticated combat behavior. But like I said, the point of this study was to look at the extremes more so than to make, the best possible viable bot. Although I think that this work does show that using things like neuroevolution and perhaps other machine learning techniques could be a more viable approach to designing bots in games. And hopefully, and regardless of whether you buy that, I'd like to think that at least some of the human observations could inform sort of design decisions in games for the future. Now, we could do a similar study like this with the more collaborative team modes, like Capture the Flag, Dominion, Assault. So that's another avenue for future research. And that is basically it. So that is my student, Adina, who unfortunately could not be here. And that QR code can lead you to one of these two links. So like all of the videos from the study are at this link, all the human screen recordings. And there's also the code for it online. And this was supported by a program called Scope, which is for undergraduate research at my university. Thank you.
Thanks a lot. Can the next speaker come in and set up while we go with the questions?
Yeah.
Yep.
So with some of the questions or ratings for yep. So you split scoring and avoidance of death for kind of two measures of efficiency of the bot at fighting, but then you kind of had helpfulness, and that's a positive attribute, and then just had two things that weren't really positive or negative. You didn't have, was it unhelpful in any measure? So it wasn't, you highlighted later in the survey that there were some inconveniences, like the bot getting too close, etc. But was that something that maybe you'd change in future questionnaires? Or?
I mean, absolutely. I mean, there's so many things you learn when you look at results like this, and you think, this is the question I should have asked. Or, because what we realize is that helpful is a terrible question, because it's too vague. Because some people thought, oh yeah, it killed the enemy better, it was so helpful. And some people thought it followed me around better, it was so helpful. We need to suss out what that means. And so we should have been more explicit and asked at least two separate questions, if not more, to like get at the specific details that we really wanted to know about. But we didn't fully realize that until after the fact. And also, to some extent, you don't want to overburden the people with questions because they get fatigued and they don't give you as good responses. But I agree, there's like a lot to learn just from the procedure and how to improve it.
Yeah, and then the findings just generally align quite well with findings for Ellie in The Last of Us, which, being a single-player game, you know, there could potentially be differences, but it seems a lot of the same things work out in multiplayer as well, about trying to not inconvenience the player, but try and just, as you said and highlighted, make them feel like the hero, really.
Exactly. And so, I mean, I definitely, I don't think it's a bad thing if we are just sort of supporting and buttressing, you know, other things out there. And so the more kind of data we can get that kind of makes these points clear, because sometimes the picture is a bit muddled, but, you know, for every new study, there's some bits that kind of crystallize or that kind of highlight and emphasize certain issues, and the more that we get reinforcement of those ideas, we should listen to what we're finding and follow up on it.
Thanks again to Jacob. And now it's me. There. Now we have Mike Preuss with an experiment on data combination. Thank you.
Yeah, thanks a lot. So this is a rather simple experiment, I would say, and one of the reasons for that is probably that it has mainly been conceived by 3 students doing a final project within my game AI lecture, and I found it so nice that actually we started to work on it and data analyze it a bit and so on. So the whole setup is, I forgot, but Georgios is not here anyway. I forgot Georgios is also included here. And David, who did the data analysis on the SVMs we also used. But more on that later. And I hope very much that the audio is working now. We try to make sure that it is. Otherwise, you will get only half of the impression, I would say. So short roadmap. A bit about facet orchestration. Just a topic that is recently coming up. There was a paper about that. Then I'll speak a bit about the test game, not too much. It's really a very simple game because it was just a 3 weeks project, so nothing much. We did an interesting experiment, and we did a survey as well as we did a self-annotation, and both were analyzed by both groups, so to say. So I present you the results on both the survey data and the arousal data, and that's basically already it. By the way, before I forget it, Jakob, there is a Team AI special issue coming up that may be matching very well with what you, for the talk, I mean. Okay. So facet orchestration, you probably know that games consist of different factors. So, I mean, this one view that was advertised in this recent paper, and facet orchestration is basically the idea that we could generate several things at once, and then we have to somehow make sure that it works together in the sense of that it is a game that humans can actually play and enjoy to play. So there are different things here. You can combine 6 in the picture, and we focus here only on video and audio. As I said, it was not intended to be a facet orchestration experiment at first, but that's what we realized when the students started to replace the audio and the video facet with completely different audio and video, as I will show very soon. So we have some hypotheses. I think there's not too much published in the area about that, and I'm not a psychologist, so there may be many things that I actually don't know about that, but still I want to demonstrate, or at least to make available some impressions from a very simple experiment concerning what happens if you combine different types of audio and video. But in our case, we have only 2 audio and video types, so to say. So you can instantly come to the conclusion or get the idea that humans may love things that match well with each other. So in our case, on the next slide there will come the visual and audio and audio impressions. So in our case we have a happy and happy setting, so happy video and happy audio, and horror and horror setting. And then you can also recombine these to have a happy horror setting and a horror happy setting. And our instant idea was, well, people will probably actually like the homogeneous setting more, because that is what they are used to. So we had no clue how they like the heterogeneous setting. And that is what the experiment is about. And then, what you can guess, at least that was also our very naive idea, that the video facet is actually more important than the audio facet. And that that the facet combinations are so different that you cannot simply learn a machine learning model on one facet and then use them on the other facets as well. So these are the 3 hypotheses. And then the test game is a simple maze game. I'll show you a video. As I said, we have 4 combinations because they actually exchanged the video and audio setting. And probably you will see more in the video. And I hope actually that the sound is working now.
We just lost.
You don't see the video? Not good. That's strange. I have an embedded one. Is it coming? Interesting. So I can. So this should be working. Alright, yeah, okay, we get it. So then I have to use the embedded one. Actually, it's not 100% synchronized, so that may be a problem. And you hear nothing, I guess. So. So now the jump scare comes. I'm sorry for that. That's why I wanted to show the standalone video. Imagine a jump scare. Okay, that was the horror setting, as you will probably have guessed. And I have only 3 videos, so you can imagine how so this is I think this is the happy setting. So it's actually completely the same game. So there are chests that have, whoop, come on. It's not playing? Yeah, now you have the audio, but you don't have the video. That's completely weird. We'll try that again. And it's 2019 and we can't play video. So there we go. So the same game actually, but just with happy. And also the audio is happy. So the aim of the game is you have about 1 minute, and you have to find the exit of the maze. That's all. And then we have in the original game we have increasing difficulty, so you can make it more and more difficult. And then there are chests, and chests can have positive and negative effects. And an example for a negative effect is a jump scare. So actually this would be a positive effect then for the happy setting. And a positive effect would be, for example, zoom out, because then you can see more of the labyrinth. It's easier to find your way out. So I try to use the same procedure now again, because obviously it doesn't play the video. So picture again, and so now we have the happy audio and the horror video. So actually it's on the web, so I will give you a link on the last slide, so you can try it out for yourself if you like. So you get an impression of what the game is like, and the question is now, how do people react? What do they like actually? Do they like to play both things? Do they like the homogeneous settings more, or the heterogeneous settings? Or whoops. So we set up an experiment. Actually, we had 20 participants. That actually takes some time because we used this device here for the PowerMate for self-annotating the arousal values. So the people got a survey, so they should actually rate which of the settings they found better. So we played 4 settings in a row, and then for each of the 2 settings they had to rate which one they found better and which one they found more difficult. And then they were also asked to self-annotate the arousal value, seeing their own video while playing. I mean, after they were finished with playing, they saw their own video play and had to annotate it. And this procedure is also described here. Yeah, I have to add that basically there are 6 possible combinations. We tried only 4 because, it would also take too long. Even in this setting, it takes more than half an hour for each participant. And if you add some time to get acknowledged to the game, it's already quite a long experiment. Okay, so what did we get? Actually, the survey results are quite interesting. There is a clear ranking you can learn from it. So lower rank is better. The horror setting was considered most fun, and then the happy horror setting, and so on. And the horror setting was also considered easier, more fun than the happy setting. So you can make up an order out of that. Concerning the difficulty, interestingly, the heterogeneous settings were perceived all the time as more difficult. So people actually cope better with the homogeneous settings, regardless if it's horror or happy. But they found it more difficult to play when it was happy horror or happy horror, yeah. Happy horror or horror happy. Okay. And we also tried to visualize this data a bit. So this is actually all the aggregated arousal data, so of all 3 second time slots over the whole period of playing. And you see that they look a bit similar, but there are some differences. For example, this is, so to say, much more constrained, consistent, the horror setting. So it's more predictable, so to say. The happy setting is also a bit more diverse than that, but far less diverse than this here. So what we can conclude from that is actually that for the heterogeneous settings, we have much more diversity. So actually, there were people liking it very much and people not liking it very much, people coping well with it, people not coping well with it. So it's very hard to predict what you get. So people had very different impressions. Then last thing, we also tried to learn SVMs using rank support vector machines and tried to actually do that separately for each of the 4 different combinations, and then try out these learned SVMs on the other combinations and look if they are matching. And what you see, so I spare you the details, but what you see here is actually the best model we got was the happy setting, tightly followed by the horror setting. So these both are comparable, and the models for everything else were much worse, so really much worse. And then you can actually use the homogeneous setting to predict each other quite nicely. So with the happy model, you can also predict the horror model, but you can much less predict the heterogeneous models, and the other way around. So here you see, for example, for the learned horror model, we can predict the happy model quite well, but the others much less so. To conclude, what did we learn of all that? I mean, we had 3 hypotheses at the start. In principle, the homogeneous settings led to more predictable, not necessarily more difficult or more fun, but more predictable, consistent reactions. Heterogeneous was considered as more difficult, but there was also a lot of diversity, a lot of variance in that values. So actually, some people found it much more difficult, some people found it the same difficulty. What was also very interesting is that the audio facet is obviously much more important than we first thought. Because we thought the audio facet is just an add-on, so to say, for the game, but it's much more important. And actually, we would consider it as more important as the video facet in this game. Maybe it changes with a different, let's say, complexity of games. For a more complex game, it may be different. And also, our third hypothesis doesn't hold. So the homogeneous settings led to better predictors for other settings than the heterogeneous ones. Generally, it's you have seen it's not, so the prediction is not very good, so you have to compromise prediction quality a bit if you use the model you learned on one of the settings for the other settings. But if you start with the heterogeneous settings and their learned model, it's even worse to predict the others. And of course, this is only a very small study. As I said, 20 people and a very small game, so there's lots to explore, I think. And if you want to do that yourself, basically, this is the web address where you can find the study itself. So you can actually, I mean, if you had a PowerMate, you could also generate values, but you can also use it just for having a look how it feels to play. And I wanted to add one thing. I hope that we still get a picture. We don't. Something is wrong here. Don't know why it's switching down. So we are going to have a conference in Leiden next year that is not strictly a games conference, but we already had a lot of games papers in there, so whatever you submit that has to do with some sort of computational intelligence, for example also neural networks or things like that, that is very welcome there. And Leiden is very cool, believe me. So I'm working there. So that's it. Thank you.
Thanks a lot. Mike, we have already a question here, and in the meantime...
Yeah, I just wanted to show the address in case that somebody wants to type it in. And,
that's a very good idea.
Yeah.
And if the next presenter can
Okay.
So anyway, I really like that, and I think it's interesting how I think that in some horror games, the designers intentionally deal with that heterogeneous nature, because like sometimes you're in a gross, like horrifying setting, but then you'll, I don't know, like if you inject a bit of happy attitude or music or something into a gross setting, it's sometimes more disconcerting. But usually it kind of shifts back. And so I think it'd be interesting to see how switching these facets affects like prolonged gameplay. So not like just one or the other, but seeing how changing it throughout the course of play affects the experience.
Actually, we had the case of the baby crying here. And when I heard that in the video, because I asked one of the students to make a video that I could show, and so I was not sure if that was actually from the happy or the horror setting. And he said, well, it's clearly from the horror setting. I mean, oh, okay. So yeah, you may be right. That could be very interesting to play with this a little bit. And if I got your question right, to change that during the course of the game.
Yeah, exactly. Yeah, because the context switches can affect the experience as well.
And definitely you can probably wake people up if they get bored, but because it's highly disturbing what you get then.
Do we have another question?
I'm curious to know how you define the horror situation or the happy situation. Are there any like a fixed criteria for picking those situations?
Actually, it came out of playfulness of students. So we didn't define that in advance, so that they had this game implemented, and then they came up with this idea where we can actually change the graphics very easily because it's just basically just a folder full of sprites. So
Yeah,
so we had no clear definition. That's what I wanted to say. So it was.
They perceive that okay, that's happy, and then.
Yeah, we saw in between, for example, there are certain effects, like you have also seen, in the happy setting, you have also seen the cats. So in the horror setting, you have the jump scares, and that is quick. The jump scares are half a second or something like that. For the happy setting, you have to invest much more time, because if you show cats for half a second, nothing happens. So you have to show that for much longer, but then you have to actually cut the game and hold it, otherwise the time runs out. So there are specific differences you have to take into account. And then I also, it's also not perfectly symmetric, because actually in the horror setting, if you open the chest and you get a jump scare, it's a negative thing, I guess. If you open the chest in a happy setting and you get these cats, it should be positive. At least that was the idea. So it's not perfectly symmetric. There are different things that could be improved about that, yeah.
Okay, thanks a lot. The next speaker is Santiago Ontañón. Is that correct?
That's correct.
Awesome. Please.
All right, thanks. So today I'm going to talk about some joint work with my student Pavan Kantharaju and my colleague Christopher Geib, and I'm going to be talking about plant recognition. So plant recognition is the problem. Imagine that you have, there's an agent and it's performing actions or is actually behaving in the world. So you can observe the set of actions that this agent is performing. And what you want to do is to try to infer what is the goal that the agent has while performing those actions, right? Like you see an agent taking boxes and putting them on top of each other and you say, oh, that agent is trying to build a tower, right? So that is plant recognition. So it has been applied to many domains like video games, robotics, so it's also used in cybersecurity to detect intruder. Like if you see some human or agent executing commands in some Unix server system, that maybe that can indicate an attack, so you want to recognize that there's a user trying to attack the system, right? So most algorithms, or many algorithms for plant recognition, are based on having some sort of formal grammar. And what they do is you have a grammar and you have the set of actions. So you basically try to parse this set of actions with your grammar. And if the grammar recognizes that sequence of actions, you have recognized the goal, right? And you can have different grammars for the different goals that you want to recognize. So whichever is the grammar that recognizes your sequence of actions, that indicates what is the goal that the agent is pursuing, right? So the problem now is where does this grammar come from, right? So this grammar can be hand-authored, which is the usual situation, or you could machine learning, right? You could learn it via machine learning. The problem is that if you learn this grammar automatically using machine learning, the grammar that comes out is very, very large and has a lot of noise, right? Like, for example, imagine in the case of real-time strategy games, imagine that we're building this agent and we want to recognize the strategy of the opponent. So we train a grammar showing it, I don't know, let's say StarCraft, showing it a lot of different human players executing a Zerg rush. There might be thousands of different ways to execute this Zerg rush. So the machine learning algorithm is trying to learn some formal grammar that would parse all of those sequences of actions, right? So the grammar is going to be very large. It's probably going to have a lot of rules that don't really matter, but they happen to be there in the data. So when you try to use those grammars for plant recognition, standard algorithms for plant recognition basically do not scale. Right? Like the grammars that come out are very large. They're much, much larger than the grammars that humans author by hand. So basically this doesn't work. In a previous work by my colleagues Pavan and Chris, they tried to apply this in the context of a real-time strategy game, and what they saw is that if the sequences of actions were longer than 4 or 5 actions, it would already blow up. Right? So with their software framework, they could not do it. So in this paper, basically, the part that I contributed, because all of these plant recognition CCGs that I'll talk about in a second is their part, and I'm not an expert on that. So I told them, how about if we replace your search-based plant recognition algorithm, like this grammar parsing by Monte-Carlo tree search, to scale it up? And basically, that's what I'm going to talk about in this paper. So a little bit of background. So all the experiments that we did in this paper were in the context of real-time strategy games, and we used the micro-RTS game, which is a minimalistic real-time strategy game implementation. It is built in Java. It's actually very easy to interface with, and it has all of the interesting features from the point of AI of RTS games, right? So they have actions are durative and simultaneous. We have very, very large branching factors. The game is real-time. If you want to have partial observability, you can set it up that way, etc. Right? Also, as I was saying, for plant recognition, most algorithms use some kind of formal grammar. And there's algorithms that use different kind of grammar formalisms, like standard context-free grammars, or there's HCN plant recognition formalisms that use these hierarchical type of grammars. In particular, Pavan and Chris, my co-authors, work in this area called combinatory categorical grammars, which are a particular type of grammar that sit in between context-free and context-sensitive. So they're an interesting trade-off between expressivity and complexity of the algorithms. And I have to admit, I'm not an expert on CCGs, but just a little bit of background so that you know more or less what are we talking about. So a CCG is defined by this triple, where we have a set of action types, like for example, pickup box, put box, right? Like our action types. We have a collection of categories, and categories are the rules with which we hierarchically combine the types of actions to form basically the expressions in the language. And then we have a mapping function that I will explain in a second. Right? So as I was saying, we have action types. The next thing is categories, and there's 2 types of categories. There's atomic categories, and atomic categories is basically for every action type we have in our language, there's a corresponding atomic category. That is just needed by the formalism. So those are not very interesting. The interesting type of categories are complex categories, which are basically the expressions in our language. For example, a category can say, if I have seen an action A, and after action A I see an action C, and before C I see an action B, then I can recognize this other type of category, right? So there's these 2 types of ordering constraints of if I see something, I expect something to the right, and that is noted by a forward slash. And if I see something, I expect something to the left, and that is noted by a backward slash. So the details are not important, but basically we can express these kind of order relations in our rules. So we have action types, we have categories, and for example, if we have, let's say, a plan of 3 actions, let me see where it is right. So we have these 3 actions here, like harvest, train, and attack. So this category here of executing the plan heavy rush, whatever that is, it doesn't really matter. So seeing train after harvest and before attack, recognizing heavy rush, that is written like this expression here in a CCG, right? So we recognize heavy rush if we see it before an attack and after a harvest. If we see a train before an attack and after a harvest, right? The notation is a little bit confusing, and I have to admit every time Pavan and Chris show me these diagrams, I get confused every time, but that's just the formalism of CCGs. And for the third element is this function f that I was mentioning, and basically every time we see an action, let's say train, this action train can be associated with many different categories, and what we have, f is basically a probabilistic mapping of if we see harvest, we could associate it with this category or this other category with different probabilities. So in this example here, every action we only associated with one category with probability 1, but there could be several. And basically trying to parse a sequence of actions is trying to find which is the set of categories with which we can eventually bring all of the actions down to a single category. Right? So that is parsing on a CCG, which is basically what the next set of slides explain. So a plant recognition problem using combinatory categorical grammar, CCGs, is defined as follows. So we have a set of observed actions. I never remember how to pronounce this letter. I'm going to call it sigma, whatever. Probably it's not sigma, but sub 1 to sub k. We have a lexicon, which is basically what I was describing before, like this triple that defines our CCG. And what we want to find is a set of goals that maybe these actions are pursuing. And for every goal, we have an explanation of why do we think that goal is being pursued. And an explanation is basically the parse tree, parsing that set of actions, right? So that is what we want to get. When we have a set of actions, to parse it with CCGs, we basically analyze the actions one by one, right? So for example, when we see a single action, which is this purple thing here, we might associate it with an atomic category, right? The next time around, if we have seen a set of actions and now we see the the last action associated with another atomic category, we add it to the group and we see if there is any complex category that can explain how this new action that we observed is linked to the previous set of actions, right? And bit by bit, we start growing this parse tree, right? And I think this is explained in this diagram a bit better than the previous one, right? So we see the first action, harvest. We associate it with an atomic category. Then we see train. Now we have a category that can associate this train and harvest to this category here, and we finally see the last action, attack, and then we can associate it with the last category, basically by trying to see if any of the things we're seeing matches with any of the rules we have in our grammar. As I was saying, the details do not really matter that much. What matters is that with CCGs let us construct these hierarchical explanations that parse the actions, right? So, as I was saying, the key contribution of this paper is that this simple grammar that I showed here is very small and very simple, but in practice, grammars can grow very large, and parsing algorithms for using CCGs are traditionally based on either A* or a breadth first search or best first search, these kind of standard search algorithms, right? And they basically search through the whole set of possible parses, trying to find one parse of the sequence of actions. So this can be very time consuming and also uses actually a lot of memory. Some of these algorithms use a lot of memory. So what we did is develop a Monte-Carlo tree search algorithm to do this parsing. So it is a standard Monte-Carlo tree search implementation with a couple of differences. So here we are not trying to find the action that wins the game or anything like that. We just try to find what is the parse tree that parses the sequence of actions. So we do not have any kind of uncertainty or opponent. So for example, if we do a playout in our Monte-Carlo tree search that happens to find a very good parse, then that is enough. We don't have to repeat it any more times, right? We have already found it, right? We don't need to do that playout again. So the inputs to our Monte-Carlo tree search is the sequence of actions. We have the lexicon, the number of iterations we want to execute Monte-Carlo tree search for, and the potential set of goals that we have to select for. In the tree, what we do is, usually in a Monte-Carlo tree search setting, every level of the tree is one player executing an action. In our case, every level of the tree is we parsing an additional action of the sequence, right? So all the nodes at depth 1 of the tree would be analyzing only one action of our sequence. At depth 2, we are seeing 2 actions. At depth 3, we are seeing 3 actions. So if we try to parse a sequence of 20 actions, the tree at most can be depth 20, right? And so the different edges or that we have in the tree correspond to all the possible different ways in which we can expand the current explanation to try to parse the next action in the sequence. Right? So in every node of the tree, we basically store the current explanation that we have at that node for all the actions we've seen so far until the root, and also the category that was assigned to the latest observed action, the average reward of all of the playouts that went through that node and the number of times we visited that node, same as in standard MCDS implementations. So we use epsilon greedy as our tree policy that in our experiments work better than UCB for some reason in this domain. Then, as I was saying, for determining the set of children of a node, we basically have all the possible explanations, or all the possible ways in which we can extend the current explanation of the current set of actions we have, given the next action we're gonna observe, right? So whenever we are growing the tree, what we do is when we reach a node in the tree that we want to expand, we generate all the possible explanations, all the possible extensions of the current explanation in that node, and then we select that one to add to the tree. For doing playouts or rollouts or simulations, however you want to call them, we do the same process. Basically, from the current node in the tree, we basically select categories at random until we have parsed all the possible actions. And the parsing algorithms for CCGs give us a probability of the current explanation to actually parse the sequence of actions. So that is our reward, and we just want to find the explanation with the maximum probability, right? Which is basically what it explains here. So to evaluate this, what we did is, in the context of a real-time strategy game, MicroRTS, we generated a training set where we had a collection of 11 agents playing this game. What we wanted to do is, given a set of, let's say, the first 10 or 15 actions of an agent, try to predict if we can predict which is the agent that was playing, right? So that was our plan recognition target here. We used Elixir, which is a software framework for plan recognition based on CCGs. For learning the grammar, we used an algorithm called LexGreedy that, given a training set, can actually learn a CCG from data. This is the set of agents that we use for generating the set of agents that we have to predict. So given a set of actions, we have to predict which one of these one is playing. We have a collection of maps. And basically, what we see is we evaluated two things. How good is our algorithm in plan recognition? And what we can see is the line at the very top here is the baseline. This is using plan recognition with the previous algorithm, breadth first search or best first search. The vertical axis is accuracy, so higher is better. And the other lines are our Monte-Carlo tree search. Of course, we cannot do better than the previous algorithm because it's exhaustive search, right? So at most we can match it. But what we can see is as we increase the number of iterations of Monte-Carlo tree search, we approach the previous approach, which is what we were expecting. But the interesting thing is that when we see the time that it takes for plan recognition, that is where the Monte-Carlo tree search approach has a benefit, the advantage. So here, lower is better. The blue line at the top is the classic approach. All the Monte-Carlo tree search approaches are the lines below, and we can see that we can grow the number of actions and as much as we want, and the amount of time or number of explanations we generate with Monte-Carlo tree search stays linear versus the previous exhaustive search approach. Basically, the time it takes to recognize grows exponentially. This scale is logarithmic. Right? So in conclusion, we developed this Monte-Carlo tree search approach for plan recognition using CCGs. So we demonstrated this can scale up better than existing algorithms. So what is interesting about this is that now we can, given a domain and just example behavior of agents, we show that we can use machine learning to learn a grammar, and then we have an algorithm that can use that grammar to do plan recognition in an efficient way, just from data. We don't need any human to author any grammar or anything like that because we can just do it from data, which is the interesting part. So that's it. Thank you.
Thanks a lot. Is there any question? Yeah, like, how would you see basically the, I'll ask the question.
By all means.
How would you see the application of the plan recognition? I would imagine it could be used in by other agents to maybe react on that. Could you see it used for analysis?
Right. So there is There's lots of different applications of plant recognition. It is used in many other domains other than games for like real-world applications like detecting intruders and things like that. But in the context of games, what my student Pavan is trying to do is if you can recognize the strategy of the opponent, then you can try to exploit it, and you can actually use it for gameplay purposes. He actually participated with some early version of this in one of the RTS competitions last year. He didn't win, but he did pretty well. So that is one way. The other interesting idea, maybe not of the plant recognition part, but of the grammar learning part from data, is you can analyze the human behavior. You can get traces of human behavior, and you can learn a grammar, and the grammar would basically tell you what are the typical type of strategies that humans deploy in this game, and then you can basically try to understand their behavior based on that.
That representation might also be used maybe for understanding like what are the different type of like strategies.
Right, exactly. Strategy discovery, yeah.
Okay, thanks a lot again. Short papers
yes.
have like short
12 minutes and 3 minutes for QA.
Sorry?
12 minutes for presentation
and 3 minutes for
Q&A.
Yeah,
okay, thank you. Can I use microphone?
You can actually use the screen if you want. So I'll try it for it works. Okay, work.
Oh. It's okay. Yes.
Okay, so the next talk will be by Yudai Tsujino, characteristic study of dense charts on rhythm-based videos. Thank you.
Thank you. Hello everyone. I'm Yudai Tsujino from Rhythmbased University, and my research is the characteristic study of dance charts on rhythm-based video games. So let's start my talking with about my research field. In rhythm-based video game, players do some actions corresponding to the song and the displayed charts. Especially we are interested in dance games, which is a subgenre of rhythm-based video games. So here is an example of playing dance game. Do you know Dance Dance Revolution by Konami? This is a video of world championship of that game. So here let's go. The audio is a little bit small, and this is a really hard example of that game. But actually, in dance game, there is many charts with many songs, from easier to harder, like you saw. So players picks a chart from enormous choices based on his or her specialty or preference. For example, the chart for song A is simple but many steps, like while charts for song B has not so many steps, but it's technical. Like this. I wonder did you find a difference of two charts? But the player, for me, I'm good at charts for song A, but I'm not good at song B. And I like song A, charts for song A, but I don't like. Though the other player has a different opinion. Even those charts are rated as same difficulty, level, every player has their own opinion for those charts. So what makes the differences? It seems every chart has its own characteristics. The characteristics made with multiple features like step frequency, the rhythm is complex, and the body movement is hard to play, or something. And the characteristics affect the difficulty level and fun of charts. So the characteristics is what we achieved through our study. But the characteristics of those characteristics of charts is not studied well. One of mainstream research related to rhythm-based video game is automatic chart generation. It is task of procedural content generation. Donahue et al. Tackled this task with a machine learning method, but they used all of the charts in the dataset. The dataset contains a mix of charts with varied characteristics. So what happened to the output? The output chart may have no characteristics because the characteristics of each chart in the dataset will be averaged through training process. It is okay if this is just machine learning task, but here is conference of games. Why don't we focus on the fun of those charts? The charts with no characteristics may be boring for players because it feels incomplete or nothing is narrative. So we have two subjects. First, what features make the characteristics of the dance charts? And second, can we classify the charts with their characteristics? That is, can we track characteristics through unsupervised clustering method? This may be useful for automatic chart generation. By using charts with specific characteristics for model training, the output chart may have intended characteristics. For example, if we used charts with many steps for training, the output may also have many steps. So this is those are our subject. I'm sorry that I have no time to talk about those two, so I mainly report about the second one. Please check the proceedings for detail about first one. Sorry. Here is information of dataset we use. The dataset has 615 charts for 133 songs. So each song has 4 or 5 charts which differ in difficulty level. The easy one for hard one. We heuristically set following features. Some features are related to the charts, score features, like step frequency, rhythm complexity, or uniqueness of step sequence, the type of arrows. And some features are related to track itself. That is song that are song features. The tempo of the song and the gimmicks set in that song. By extracting those features from each chart, we made a feature vector. We combined those features into one vector and apply. Sorry. We combined those features into 4 types of feature vector and applied principal component analysis to transform them and create it. And finally, 229-dimensional feature vector is obtained for each chart. And finally, we conducted k-means clustering with the number of cluster k is 4 and 6. Here is a result table. It was confirmed that there are majority clusters with 100 charts or more. Cluster ID is 0, 1, and 2. And there are minority clusters with 25 charts or less. Cluster number 3, 4, and 5. The result was similar between k equals 4 and k equals 6. So we will discuss about the result with k equals 6. For majority cluster, cluster 0, 1, and 2 differ in the step frequency and rhythm complexity. Here is an example of charts belongs to cluster 0. Oops. Like this, the charts in the cluster 0 have around 1 steps per second. And its rhythm is simple, mostly fourth note downbeat rhythm. Charts in cluster 1 has more steps than charts in cluster 0, like this. And the rhythm is also more complex, like pam, 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 pam. Some eighth note upbeat rhythm. And on cluster 2, there is many steps in the chart, and 16 note rhythm are frequent, like this. It looks so hard. So we confirmed that step frequency and rhythm complexity would make up the characteristics of charts. And move on to minority clusters. The charts in cluster 3 is charts for high temp tracks. Okay, like this. The scroll speed is so high. can't see what's going on. Like this. And cluster 4 has only 2 charts, which rhythm is shuffle rhythm, like this. Stat, 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 stat. So this is so specific for those 2 charts. No other chart has the rhythm like this. And finally, cluster 5 has only 1 chart, which is so specific step sequences. It contains a strange kind of step. Did you see? There is three arrows in same timing. Why we have only 2 legs? Why we should do so? I don't know. So we are so happy that we found those highly characterized charts. Those are really rare. But those are no longer clusters. It has only 2 or 1 charts in that cluster. So these are assumed as outliers. We should assume as outliers. So this is our conclusion, and one of our future work is the outlier charts should be removed in advance to avoid such minority clusters. So this is end of my presentation. Thanks for paying attention.
Hello there. I really enjoyed this presentation.
Thank you.
It was amazing. Thank you very much. I have a question about the clustering. Since you have a sequence of actions that come in, there's a sequence and at the same time it can be parallel actions at each step. I was wondering if you have considered using some sort of sequence mining techniques for extracting features or sequence-based sort of k-means. Sort of to track sequences, to capture those sequences, instead of capturing the full, patterns within a session. Or maybe that's something, if you haven't, maybe that's something that...
Actually, I didn't know such technique to track sequence data for clustering. So I would consider in future work. Thank you for sharing information.
Actually, I'm a co-author. Sorry. Actually, we use a trigram to add the features of that vector. So probably that is a kind of the simple features to capture the sequences. Yeah, maybe that is all just a 3 sequence. Yeah. Thank you. If there is no other question, thanks a lot.
Yes. Can you help me with the mic?
Sorry?
The mic.
Yeah.
You can use this one.
Thank you. Yes, please.
Just clip it.
Right here, I suppose.
Yeah.
Just. It's going to be what?
You can clip it like in your pocket or whatever.
Okay.
Okay.
But
It's around 12 minutes plus questions.
yes, I'm just waiting for this to start. Any idea? Yeah. It's okay? Yeah, it's okay.
Yeah, probably a little bit closer, yeah.
Closer. Now. It's fine?
Okay, so the next talk will be by Omar Verduga, correct?
Yes.
Thanks a lot.
Okay, thank you. Well, hi everyone. My name is Omar Verduga, and I'm doing my PhD in Dynamic Learning and Decision-Making Lab here in Queen Mary, experimental psychology, by the way. And I'm looking for ways in exploration and exploitation, but from a human perspective. So in this context, I'm going to define exploitation like making the best decision given the current information, and exploration like the act of gathering more information. One example, for instance, is you want to go out and eat at some place, and you need to select a restaurant. So you're faced with this dilemma. going to the usual place, which is exploitation, or you want to try a new restaurant. And let's say that that's exploration. Now, exploration and exploitation represents two mutually exclusive goals. And how humans solve this dilemma, this is still an open question. Experiments provide divergent evidence about what kind of strategies humans follow. But at the end, humans have to be good enough to survive and reproduce, and we don't need to reach optimality in an ever-changing world. And even if humans don't often reach optimality in the decisions made, our behavior is still reasonable, good enough to achieve goals over time with a dynamic environment. So, if I want to test my ideas in a dynamic environment, some characteristics that I find interesting are, well, in a dynamic environment, one agent interacts with variables that change in real time, both as a consequence of agent's actions and autonomously. Also, the desired goal usually is not, cannot usually be achieved in just one step, so you need to plan a series of steps to come closer to your goal. And the multiple decisions to deal with this system receive different form of feedback. For instance, positive feedback, negative feedback, delayed feedback, or even random feedback. And, well, one kind of dynamic environment that is really interesting are real-time strategy games, right? Which are based on this philosophy about the 4X, which means explore the environment, exploit your resources, expand your economy, and exterminate your enemy. And I think that everyone here knows that we are dealing with a large action space when we are dealing with real-time strategy games. The players can issue actions simultaneously. They have durative actions, and you are dealing with partial view of the world, and also you are dealing with fog of war, which basically means that you are dealing with imperfect information. So, I was trying to run these experiments to test exploration and exploitation in humans, and I have some options. The first option is recruit participants using Prolific or Amazon, mechanical Turk, and then create a custom-made experiment with Gorilla, PsyCopy, PsyToolkit, and then analyze the data, as usual. Or recruit participants and then run the experiment in a lab-based setting. And, well, I need to create the experiment in Unity Experiment Framework, DeepMind Scilab, or Custom Quest StarCraft. And then analyze the data. Or I just simply collect existing replay data that you have. So I'm going to the company or these communities, and they will provide me with large data sets. But every choice that I have here has a problem. For instance, if I'm recruiting online participants, usually the environments are not complex. If I run in my experiments in a lab-based setting, the scale is not good. I'm not going to recruit a lot of participants. Or if I analyze the data and existing replay data, well, the problem here is that I'm not able to manipulate some conditions, some experimental conditions for new findings. So I came with this idea of like, okay, let's use a real-time strategy game to collect experimental data, but running it via web. Why use real-time strategy games? As I told you, because explore and exploit are part of the mechanics of the game. And we have clear objective measures of success, observational data. We have a lot of engagement from the participants. They are actually enjoying playing games. Likert scales sometimes are not good enough for our experiments. So show, don't tell, or like David Melhart said in the first presentation, our gameplay says it all. Why not use current data sets? We need precise control over the experimental settings, meaning conditions and manipulations. And why run it via web? Well, we need to run a scale and outsource the recruiting part, because we are interested in recruiting hundreds and thousands of participants fast. In data, the more the merrier, right? So in this panorama, let's say, our tool fits right there. It's based on HTML5, JavaScript, PHP, MySQL. I mean, it's pretty generic in that aspect. Important features, okay, I'm saving the state of the world, the mouse clicks, keyboards event, the state of the agents, the historical position of the agents while they are moving. And I'm introducing 3 types of agents, which are the Explorer, which is a human-controlled agent that collects resources. A Competitor, which is basically like Explorer, but is AI-controlled. And they are looking for exactly the same resources. And a Predator agent, which is an AI agent that is trying to hunt explorers. So, testing our tool. We run this experiment. We recruited the participants through Prolific. We got 300 participants in 6 hours, which I think that is a good number. And after the data cleaning process, we got 248 participants. £5 per hour, but the actual session was way shorter. And the participants answered risk profiling questions, but in-game. It's not like they are doing the survey data after the game or prior to game. I'm going to show you. Okay. So this is the setting with total visibility. And this is the setting with partial visibility. Now, the question for our experiment is how much the competition and threats shapes our exploratory behaviors. The visibility manipulation is just these 2 things. So total visibility or partial visibility. I think that is pretty clear which one is the one corresponding. And also I'm defining these exploitation points, which are the points where I'm leaving the resources, right? So in the first condition, I'm just leaving the participants gather resources without any other agent and with total visibility. So we can see that they are just exploiting the knowledge, exploiting the environment. If I introduce this manipulation about visibility, they are forced to explore a little bit more to gather information. And now, the important part, when I introduce agents, well, let's go back on this. If I introduce a predator agent, as you can see, the exploratory behavior suffers. You don't want to explore. If you introduce competition, you're forced to explore more. And if you are in the condition with predators and competition, it doesn't matter. They just want to explore more. So, findings. When you are not using other agents, total or partial visibility is not that important. We are suboptimal, but it's good enough. We are not that bad. But if you introduce agents, the threats make the exploration suffer, and competition motivates you to explore more. So future work in this case, API to communicate with the MicroRTS, a graphical designer tool to create new experiments, the verbosity of data logs, because for this 15 minutes, each participant is giving me 10 megabytes of data, more types of units because I need soldiers to kill somewhere else, and player versus player mode because I want to run some experiments in behavioral economics. And just, well, the fuck thing is, why not just create a custom StarCraft? I need to collect from a lot of participants. MicroRTS is exactly the same problem. I don't want to use the same data set that everyone is using because I'm testing small manipulations, small conditions. And also because I'm including in-game service as a part of the manipulations. And, well, there's a link for the code. The code will be released next week. And I suppose that's all. Thank you. Thank you.
We have like a couple of minutes before the break. So if anyone wants to ask any questions, yes?
How deterministic was the location of the resources?
In my experiment, it's totally deterministic. I'm saying, okay, I need these 7 positions, and the random thing is how many resources do you have at each palette?
Maybe to follow up that do you think that could affect like the specific location of your like experimental design? Do you think it could affect the behavior of the users somehow, or?
In fact, that's the next experiment that I'm running, and I suppose that it's a good thing to research. So I'm in the middle of that.
Okay.
Something else?
Okay, thanks a lot.
Oh. It could be over the coffee break.
I was going to say, I may have missed it. Were participants pre-warned in the partial visibility case that predators or competition with predators, that they need to discover that themselves and explored in the environment?
Sorry, say again?
In the case of partial visibility, were participants forewarned that predators or competitors were there?
No, they were. I say, okay, maybe you will face some other agents in your environment, but I'm not saying that it's going to be a competitor and predator or something else. Or maybe it's not, there's not. I'm just saying, okay, maybe there are agents. I'm not stating clearly which kind of.
I was wondering if knowing it ahead of time what you would like to face, or what you will face, it would adjust their strategies. Because if I know there are predators, I'm likely to be a bit more cautious.
Yeah, I'm not saying that.
Yeah.
No, I'm not saying. The second experiment, I'm just saying, okay, these things are not artificial agents, are humans. It's a deception experiment. That's it.